Are you ready to go for the on the final? So I'll send the review for the final on Wednesday. Then I'll make sure I grade your exam by Friday. You should get your exam. Okay, so exam 3. So Wednesday. Final exam. Final exam is comprehensive. So I'll send the review of the final exam, but it's actually just like what we did in exam 1, exam 2, and we do in exam 3, and section 5.1, 2, and 3. So the final exam will not be hard as long as you review on 1, 2, 3, section 5.1. So exam 1, exam 2, exam 3, and 5.1, 5.2, and 5.3. So this is 150 points. 150 points. This is still 100 points. 100 points. So you should remember that exam 1 is 100, exam 2, 100, exam 3, 100. Final exam, 150. So final exam, 150. Homeworks is 50 points. So the total of 500 points. So this is actually not like the percentage. So the percentage can be fair, but this one may not be so fair. So make sure, in this case, every point matters. So every point matters. So make sure you write something in your exam. Do not leave it blank. So if you leave it blank, then of course you will not get anything. So try to write something. If you don't know anything, so you make sure you try this. And then there is a review of the course. So if you when you review the course, then let me know, and then I'll give you five points in homeworks. So when you review the course, write an email that you reviewed that and in homeworks. So if you're doing well in your homeworks, then of course you'll get 50 out of 50. So 5 points in your homework when you review the course. So the review is on the far right. So just review. I'll not know whether you reviewed or not, but make sure you review it. Try to review it. And then you just write an email and then let me know when you review. So you'll get 5 points in your homework. So if you had 45 in your homework, then you'll get 50%. Okay. So I want us to try finish this course. I want to use 30 minutes and then the 20 minutes remaining, then we can go through the exam. Okay, so let's try complete this one in the next 30 minutes. And then we go through the exam. So if you have any question, So I'll have my office hours anytime, as long as it's not late at night. So you can email me anytime you have any issue from today up to exam time. Okay. All right, so let's look at the last section, which is diagonalization. Of square matrix. Diagonalization of a square matrix. So let's define this. So let's do some definition here. If we let A to be an n by n matrix, we let A to be an n by n matrix. One, a diagonalization of A is a decomposition A, which is equals to P d P inverse, P d P inverse, where D is a diagonal n by n matrix, and P is an invertible n by n matrix. P is invertible n by n. 2, we say that A is diagonalizable if A has a diagonalization. If A has a diagonalization, then theorem 2.2, then theorem 2.2. An n by n matrix A is diagonalizable invertible matrix is a diagonalizable, matrix. A diagonalizable matrix if and only if A has exactly n linearly independent eigenvectors. So you see, you remember we said if this is diagonalization, then if A equals PB, P inverse, then we say A is similar to what? A is similar. So if A is diagonalizable, then A is similar to B, and B has n by n is an n by n matrix. And if this B is an n by n matrix, then it is a diagonal matrix. It's actually a diagonal matrix, which can be, so if this is a D, so D can be A, and then we have the values here along the diagonal here. So we have the values along the diagonal. And here are zeros. So if the values along the diagonal are not zeros, then therefore we have the pivot position in each of the columns and the rows. So if we have the pivot position in each of the columns and the rows, then definitely if it is an n by n matrix, then we have n linearly independent vectors. So we have n linearly independent vectors, n of them. So we'll not prove this theorem, so you can check in your book. So let's look at the procedures on how to diagonalize a matrix. So the 2.2 procedures, 2.3 for diagonalization. So let's look at the procedure for diagonalization. We let A to be an n by n matrix. We let A to be an n by n matrix. Number one, find all the eigenvalues of A and their multiplicities. So that is the first thing we need to do. Find all the eigenvalues of A and their multiplicities. Number two, find a basis for the eigenspace corresponding to eigenvalues. Corresponding to eigenvalues. Number three, determine whether A is a diagonalizable or not. If A is diagonalizable or not, by comparing the dimensions of each eigenspaces with multiplicities of the corresponding eigenvalues. Corresponding eigenvalues. And then lastly, number four, construct an invertible matrix P and diagonal matrix D such that A equals to P D P inverse. So those are the procedures on how to diagonalize A. So number one, you get the eigenvalues. Number two, use those eigenvalues to get the eigenspaces. So this is for eigenspaces. So each of the eigenvalues. Number three, determine if A is diagonalizable or not in accordance with the eigenvalues. Then finally, from those eigenspaces, then construct P. And also, this P is just coming from the eigenvalues. This P is just coming from the eigenspace. Okay, example number one. So we use an example to prove this. Example. So find the diagonalization of each of the matrix if possible. So let's do an 3 by 3 matrix, which is 0, -4, -6, -1, 0, -3, and then 1, 2, and 5. So I'll use this one as an example of all of the. So the first thing you need to do is you need to get the eigenvectors. So the first thing is number one, find the eigenvalues of A and their multiplicities. So we have that A there. So how can we get the eigenvalues of A? How can we get the eigenvalues of A? So if you remember, we want to determine the determinant of A minus lambda. In this case, it is a 3 by 3 matrix. So we want to get the determinant of this. So we want to get the determinant of that. And the determinant here is giving us the characteristic polynomial. So once you get the characteristic polynomial, then now you convert this to characteristic equation, whereby you equate that one to 0. So you equate that one to 0. And then you now get the values of lambda. Get the values of lambda. So in simple terms, what you do here, you subtract the diagonal matrix by what? By lambda. So the diagonal entry, sorry. So in this case, this will be 0 minus lambda. So it will give us minus lambda. And then the other one is -4 minus 6. This is -1. 0 minus lambda is minus lambda minus 3. and then this is 1, 2, and then 5 minus lambda. And then you do what? You actually get the determinant here. Are we together? So instead of writing the whole thing, yeah, then we just have say 0 minus lambda, 0 minus lambda, 5 minus, and then you get the determinant. So here you can use the first row or the first column. So we can use the first column. So here you can say then the determinant here will now be minus lambda, and then you close this and that, so minus lambda, minus 3, 2, and then 5 minus lambda. You can actually use the first column here, the first row, and then minus, we know this will give us a minus, and then minus 4, and then close this and that. So minus 1, minus 3, 1, and 5 minus lambda, and then plus minus 6, and then what remains is minus 1, minus 1, minus lambda, and then 1 and 2. So finally, what you will get here when you go solve this is you'll get minus lambda minus 1, lambda minus 2 squared. Lambda minus 1. So this is our characteristic polynomial. So that is the characteristic. So basically, since this is the 1, 2, 3. So it is a 3 by 3 matrix. So the number of eigenvalues should be what? So this is a characteristic polynomial of what? 2 plus 1. So the number of eigenvalues should be, or can be 2, or depending on the number of multiplicities. Then our characteristic equation, then we equate this one to 0, which is equals to minus lambda minus 1, lambda minus 2 squared. Now, using the 0 product property, then this lambda minus 2 is the same as lambda minus 2, lambda minus 2, right? And then the other one is minus lambda minus 1 there equals to 0. Using the 0 product property, then lambda minus 1, which is minus here, equals to 0. And then lambda minus 2 equals to 0, lambda minus 2 equals to 0. So here, definitely, this lambda equals to 1, lambda equals to 2, and then lambda equals to 2. Equals to 2. So therefore, our lambda 1 is equals to 2, and then with multiplicities, multiplicity 2, and our lambda 2 equals to 1. Any question? This minus here. This minus, you can divide everywhere by minus, right? So you still get this can cancel with the minus. This is 0 divided by minus. 0, of course. And then the lambda, you get the lambda because you take this one to the other side. Take this to the other side.
It's not going to
What's that?
does not change the sign of 1, 2 plus before we
Okay, so if you open this bracket here, then you will still get minus lambda plus 1 equals to 0, right? Check this one to the other side, which is the same as minus lambda equals to minus 1, right? And this cancels with that. So you get lambda equals to 1. Okay. Any other shortcut? So we have lambda 1 equals to 2. Since these are two of them, so with multiple equals.
Where did you get the lambda minus 1 and the lambda minus 2 squared?
Okay, so when you we can expand if we have time, but actually we don't have time. So what you do, you get a determinant here, right? And then you multiply by this. So getting the determinant here, you multiply this and this and this and this, and then multiply by this. You get an equation here. Again, you do the same thing here, you get an equation. You do the same thing here, you get an equation. Once you continue like that, you will reach a point where it will be of this. The equation will be like this, okay? Yeah. If you have any issues, we can work on it later after class. So you go try. If you don't get this one, let me know. Okay. So that is what you get. Now, and then you now come and now go to step number 2. And step number 2 was now find the basis for the eigenspaces. Now find the basis. So find basis for eigenspaces corresponding to each eigenvalues, corresponding to each eigenvalues. Now we come back to this A minus, now starting from this first one here. So minus 2 lambda, sorry, minus 2 I3, and then x equals to 0. So we want now to solve this. So we want to solve it. So we need to solve. So we want to get the values of x when lambda is 2. So then, in this case, then just like the way we did with the lambda here. So you replace this lambda here by what? By 2. By 2. So our new matrix then will now be minus 2, and then minus 4, minus 6, and then minus 1, minus 2, minus 3, 1, 2, 5 minus 2 is 3. And then x equals to 0. X equals to 0. Okay. So where there is lambda here, we replace by 2, and then 2. So starting from the first. Then now we want to solve. So to solve the values of x, then we now write the augmented matrix, which is minus 2, minus 4, minus 6, 0, minus 1, minus 2, minus 3, and then 0, and then 1, 2, 3, and then 0. So that is our augmented matrix. Then we do what? We now reduce. So we now reduce this matrix. So when we reduce this matrix completely, then what we get is 1, 2, 3, 0, 0, 0, 0, 0, and then 0, 0, 0, and then 0 there. So you actually start by switching. You switch R3 and R1. So you switch R3 and R1, and then you use. So switch this and that. So that is what you will get. So therefore, we have our basic variable as x1, and our free variables are x2 and x3, x2 and x3. So our new linear equation here will be x1 plus 2x2 plus 3x3 equals to 0. Then x1 equals to minus 2x2 minus 3x3. So our solution set is our x equals to x1, x2, x3, which is equals to x1 is minus 2, x2 minus 3, x3. x2 is our free variable, so x2. x3 is also our free variable, x3. Okay. And then finally, this is equals to factor out x2, x2. We have minus 2, we have 1, and then 0. Plus x3, then we have minus 3, 0, and 1. Any question after that? Any question? So if you see this, that is actually what we get. So basically, then the eigenspace now is the span of what? The span of minus 2, 1, 0, and minus 3, 0, and 1. So that is so on the eigenspace for the first one. Now, when lambda is equals to 1, lambda is equals to 1, then you do the same thing. So you replace the lambda by 1, so you get minus 1, minus 4, minus 6, minus 1, minus 1, minus 3, 1, 2, 3, this will be 4. Do the same thing, you replace lambda by 1, minus 1, and then 5 minus 1. Then you write that in augmented matrix form 0, 0, 0, and then you reduce completely using the same thing. Switch 1 and 2, and then reduce completely. Then what you get is, so what you should get is, so you should get 1, 0, 2, 0, 0, 1, 1, 0, and then 0, 0, 0, 0. So that is what. So here, our basic variable is x1 and x2, and our free variable is x3. Free variable x3. Okay, so our new solution set here is x1 plus x2, x2 equals to 0, and then x2 plus x3 equals to 0. Then x1 equals minus 2 x2, sorry, x3 here. And then x2 equals minus x3. So solution set is x equals to x1, x2, x3 which is equals to minus 2x3 minus x3, and then our free variable, which is x3. So then this is equals to x3 minus 2 minus 1, 1. So for any x2 and x3, for any x3. So then, therefore, finally here, our eigenspace is the span of minus 2, minus 1, and 1. So that is 1. So we found the eigenspaces. So finally, then you can write like this. So our eigen value, and then we have our multiplicities, and then we have our eigen vectors. So our eigen values here are plus 2, multiplicities are 2. Our eigen vectors that we got are 2 minus 2, 1, 0, and minus 3, 0, and 1. And then when eigenvalue is 1, multiplicity is 1, our eigenvector that we got is minus 2, minus 1, and 1. So that is what you. So finally, we get our P from our eigenvectors. So our P are these values here. So now it will form the vectors minus 2, 1, 0. The other one is minus 3, 0, and 1. And then the other one is minus 2, minus 1, and 1. And then a diagonal matrix will be formed from the eigenvalues. So you take it in accordance to how you've written the eigen vectors here. So our diagonal matrix will now be 2, 0, 0. The next one is 0, 2, 0, and then lastly 0, 0, 1. Okay. So D, we get it from eigenvalues and then from P. So if you get the eigenvectors and the eigenvalues, as long as they are of the same number, like P and this, so it should be similar to the dimensions of D should be similar, even the dimension. So once you get those, once you don't have to prove it again, whether A. You don't have to prove whether A is equals to P, D, P in, as long as you've gotten this and this, then you're right. As long as, because what you need to do to prove this, then you need to find the inverse.
You always order it the highest multiplicity is first.
No, you don't have to.
So you can switch it.
You can switch it so long as if you start from this, of course you'll get this one for the first one. Then you start from this, you put it here. But here you should put this one here. Okay. You should start from this one. And then you will switch. You will bring this here, then you should switch this and this. Okay, we will do more examples on Friday, and then we do a review of the final exam Friday. So we'll do like 2 examples and then we do a review. Okay, so let's go through this exam. Yeah. Okay, so let's go through. It's actually not very hard. So make sure you just study your notes and maybe part of your homework. But actually everything just comes from your notes. Okay, so the first one is so easy as long as you remember how to get the column space. So actually the column space, if you look at number 2 here, like this number 2 here, they have already done it for you. So the reduce to echelon form is this B here. So when you reduce it to B, the ones which are having the column, the pivot along the column, those will give you the column, the basis for the column. So now this is the pivot, and pivot here. We now come and take this, and this. There's the what? The basis for the column. Okay. The basis for the null space, once you break here, then you need to reduce this one completely. Okay. So you reduce this. So once you reduce this completely, then you solve. You now solve. Actually, you add 0, 0. You're actually solving AX equals to, you're solving AX equals to 0. Okay. So this is A, and then it has been reduced to this one. So you just come and add zeros here. Okay. And then you now reduce completely. So to reduce, you reduce this one completely, and then now you find the values of X, which can be values here. So those which you get here, the vectors which you get here are the null spaces of A. The dimension are the number of vectors. So the dimension in this case, for since it's easy to see, this and this and this. So the null space you get the dimension once you solve. And then the graph is the dimension of that. Any question? Okay. So compute each of them. We should remember how to use that. 4 factors, if you remember, then if you want to get C11, then this is equals to -1, 1 plus 1. Okay. And then A1, 1, A1. Okay. So you close in accordance. So you actually this one, you close in 1, the first column, the first row, first column. So that is the 4 factors. So C111 is the number of the one which you have 1 and 1. Then and then you also pick the one which are as many zeros as possible. So in this case, you can pick along this column. Then close that, and then also you come and pick again to get to the next one, go on just as many zeros. Again, you also did a process for this. You know, you use this. Then, what about the A inverse? What about the inverse? Inverse again, you can use the cofactors. So what you do, you get a cofactor C11, C12, C13 up to the end. So C11 like that. And then you do what? So you make sure it transposes those cofactors. So these, the one which is C11, C11, C12, C13, yeah, are becoming now the what? The rows. The next ones to be the next row. Yeah. Okay. And then you divide by 7. So the A inverse is equals to one all over determinant of A, and then the adjoint. Actually, we're looking for that, the adjoint of A. Adjoint, we get it from the cofactors. We get it from the cofactors. Anyways. So all these things have them in our notes. So we go through. Okay, number 3. Make sure you remember how we were doing the row operation. If we switch the rows, then determinant becomes the what? Negative, right? Determinant becomes negative. So if we switch this row and this one, then our determinant will be. If we multiply by, let's say, like what they have done. We have done here. If we multiply by -2, yeah, then this is similar to factoring out -2, and then you get a determinant of A, B, C, D, E, F, G, H, and I. Determinant of that. And determinant of this is what? Is 3. So our determinant here is -6. So you factor out -2. So this you're switching. So this is equals to -3 since you're switching the second row, the third row. So any manipulation on addition or subtraction, then it's still giving you the same. It still gives you the same. Okay. Number 5, use the determinant to determine whether the vectors are linearly dependent or independent. So we say if it is linearly dependent, then the determinant is equals to what? If it is linearly dependent, then it means this is what? Singular. Singular. Okay. So if it is singular, then it means that the determinant is equals to 0. So for it to be linearly independent, then the determinant is not equals to 0. So it is invertible. So if it is invertible, so actually it is invertible, and also determinant is not equals to 0. Determinant is not. Okay. Right. So let me remind you, this one is still an example. Okay. Something similar to this. in your exam. So you remember that. Okay, so determinant of AB is the same as determinant of A, determinant of B. That is easy. Determinant, this one is the same as determinant of A. Determinant of A transpose is the same as determinant of A. Determinant of A inverse is the same as 1 all over determinant of A. Actually, we have them in our notes. Determinant of this one is the same as factoring out 2 and then raising to what? If this is a 3 by 3 matrix, then you raise this one by 3, determinant of determinant of A, right? We have the T R. So in factor out this 2 here, this is a 3 by 3 matrix, x by 3, and then determinant of. So what you get is 2 is 3 multiplied by 2, which gets 16. Right? That one is hard. Determinant of this one is the same as this is the same as determinant of A, determinant of B, and then multiply by determinant of A inverse is the same as 1 over determinant of A. And this cancels with that. And then we get determinant of B. Which is what? Okay. All right. So if you have any question, free anytime.
Can you post the solution?
The solutions are at the back.
Are they on the back?
Yeah.
Okay, thank you.
The solutions are. You also have this one in Moodle, so you can still put it. Okay, if you have any question, I have my free time anytime. You can write an email. Then we can schedule a meeting. So all the best in your exam.